So our next talk will be from Dr. Gerard Holzmann. I have to share that Gerard usually gives the keynotes for this event. So this talk is as good as a keynote. I just want to let you know. If you've seen, if you go to our website, flightsoftware.org, and look at the previous years, you'll see that I think almost every year Gerard is giving a keynote. And so this is a really great talk. So Gerard, welcome.
Yeah, no pressure. Okay, so I submitted a talk this time because I actually have something to say. I wanted to talk about the quality of testing. So I'll ask a couple of questions and then try to give an approximate answer to these questions. First question is, how good is unit testing if you achieve 100% MCDC coverage? This is the modified condition decision coverage that typically is required in standards like DO 178B and C. And it's the typical target for flight software development, and actually only recently, right? So before MSL, I don't think we had a target for test coverage, but so we now have that, and if you've tried to achieve that in your software, you know that this is very hard to do. And managers are extremely pleased if you get close, right? If you get 95% or thereabouts, then everybody is very pleased because that is very, very thorough, or at least difficult to achieve. Second question is, if you do randomized testing, can you improve? Can you actually do better? Third is, what if you use testing with perfect recall? And I'll explain what I mean by that. And then, you know, maybe can we exploit parallelism to increase the coverage of our tests or to get more test coverage in a shorter amount of time? And the quote from De Morgan is the obvious one. If you try often enough, you should be able to succeed in anything that you try to achieve. So let's start with the first one. And let me give you three very, very small examples to illustrate what MCDC coverage actually achieves. So here's a first example of a very tiny C program that has two conditional tests in a row. If you draw the control flow graph, it looks like this. And obviously, there are 4 paths through this graph. Now, you can achieve 100% MCDC coverage by just doing 2 tests. One following the red arrows and one following the green arrows. There's a bug, though, in this program that is not revealed by these 2 tests. So if you do the test with argument 0, 1, and you fail to set P to the address of X, and you try to dereference P in the second conditional, and you crash. So you achieve 100% MCDC coverage, yet you miss the bug. And actually, you only have about 50% coverage of the control paths, the execution paths in this little program. Now, this is just 2 conditionals in a row. If you have 10 conditions in a row, the number of paths goes up to 2 to the 10, and you can achieve, again, full 100% MCDC coverage with 2 tests alone, taking all the right branches or taking all the left branches. But your actual coverage is just a tiny fraction, like it measured differently in terms of execution paths. Here's a second example with a loop, very, very simple loop, where here we loop by setting elements in an array up to some limit that is determined by the arguments x and y. Of course, it's a silly, artificially constructed example, but that's the control flow graph. You can do 1 test and achieve 100% MCDC coverage, and you'll miss the obvious bugs. And actually, there are 2 to the 31st possible executions of this program, right? Because x plus y could add up to any integer number. If you test only 1, you hit all the statements, and you're done. Your manager is pleased, very pleased, right? 100% coverage. Yet you don't find the bug. Third one, if you use threads, you use a multi-threading environment like we do in most of our flight software. Here I try to create just 3 threads of execution with 3 statements in each thread. And the reason I pick 3 is because it's easier to visualize what the execution space actually is. So there is 3 threads of execution. They can be interleaved arbitrarily in time. So you can do first all the blue transitions, or all the red ones, or all the green ones, or anything in between, like one blue followed by a red, followed by a blue, followed by 3 greens, etc. So basically you walk a cube. That's why I picked 3 for 3 statements, 3 threads. There are 1,680 paths through that cube from the upper left corner to the lower right corner. If you just do one execution and hit all the statements, you have achieved 100% MCDC coverage. But you've only executed really like 0.1% of the possible execution paths. There could be 1,000 errors in this thing, and yet your chance of hitting that is not, well, actually, if there are 1,000, your chance is pretty good. But if there's 1 error in this, your chance of hitting it is very, very small. So there's 3 examples where MCDC coverage, the 100% number, is very misleading. So maybe that's not the best metric to aim for. So the question is then, many people propose randomizing testing so that you can at least get an unbiased sequence of tests. So we can look at that. So here I have a randomly generated graph of 100 nodes and 200 edges. Turns out from the node in the upper left, node S1, there are only 83 nodes actually reachable from that. Question is, how many random tests would you have to do to be certain, or to be reasonably comfortable, that you've visited all 83 possible states that are in this graph? So this graph can be the control flow graph from a system, like after interleaving from multiple threads, control flow graph for any type of function that you're trying to test. So the question is, how many random tests do you have to do? So forget about it. We know MCDC coverage is not going to get us where we want to be, not sufficiently far. What if you randomize the whole thing? Well, I did that experiment for that particular graph. I did n random tests, so 500 steps, so to at least have a limited test length in case there are cycles in this graph, which there are. And then you can plot. Okay, if you do 10 tests, you hit 70 states, but most of them are repeat visits to those states, so there are only 5 unique in that set, and that's 6% of the total. You have to do 100,000 of these tests, these randomized tests, to be reasonably confident that you hit 100% coverage, that you've visited all the nodes. So if you increase the size of the graph, here's a randomly generated graph of 1,000 nodes and 2,000 edges. 781 states are now reachable from the initial state. If you do that again, you see that even if you do 100,000 random tests of 500 steps in this graph, starting at the initial state, you still don't reach all the nodes. You reach 775 out of 781. And so the number of random tests that you have to do goes up exponentially with the size of the graph. So that also doesn't sound very good, right? So it is the plotting the coverage in the bottom, and the number of states that you visit at the top, but actually the number of uniquely different states is much, much smaller than that. So now the benefit of a randomized test is completely unbiased. It doesn't look at documentation or what somebody tells you the system is supposed to do. It'll just blast an application with test data, and very effective in shaking out bugs. But in getting actually complete coverage of the execution graph, it is not particularly good. So now, is there anything else that you can do? The question is, if you could remember where you've been, like if you visit states, so it's the traveling salesman problem. If you can remember where you've been, you can avoid going back to the same cities over and over again. So what if you did a depth-first search or a breadth-first search in those same graphs that I just showed you? So here's a depth-first search, a breadth-first search in the first graph of 100 nodes. You do one test, you visit all the states, guaranteed, and you have 100% coverage in a fraction of a second. I did plot actually how long the other test took, right? So in time, this is hours, right, for 100,000. So in a fraction of a second, you have all the nodes. But you have to be able to remember everything that you've seen, right, so that you can systematically generate the graph. For the bigger graph, this is the breadth first tree. Again, in a fraction of a second, you visit all 781 reachable nodes from the root, no repetition. The only thing is you have to be able to remember which states you visited. And you just do a standard. You can either do a depth first or a breadth first search. In this case, breadth first search leads to a shorter graph, of course. You have the shortest path to every reachable node. So that sounds incredibly attractive, right? Because it solves that problem that MCDC coverage doesn't really give you 100% coverage of the execution graph. And it solves the problem with randomized testing where you keep repeating over and over and over, visiting the same states that are close to the root. So that seems, so how would you be able to set that up? Now the question is, so I said you have to be able to remember where you've been. And I called that strategy testing with perfect recall. The question is, does it actually have to be perfect? What if it's not perfect? What if this graph that you're searching is much larger than what you can actually store in memory? You would have to store these states in memory, and your memory is only finite, right? And if you have a really complex system, you will run out of memory. The good thing is that it does not have to be perfect. Any amount of recall will help. So you can store just a hash signature of a state. If you store a 64-bit hash of every state, you have very, very thorough matching of states, the recognition that you've tested something before. You can even hash down to a Bloom filter where you store just a single bit per state in a fixed size Bloom filter, and it'll speed up your search tremendously and increase your coverage immensely. Doesn't have to be perfect recall. Any amount of recall will help. So the picture just shows how a Bloom filter works, where you come up with a number of hash functions potentially. You have the keys, which are the states that you're visiting, and you set certain bits in the Bloom filter to indicate that you've seen a particular state before. And so in this case, there are 2 hash functions that are used that set 2 bits in a Bloom filter. And if you see those same 2 bits set, then you can be reasonably confident that you've seen that state before, with occasional misses, where you think, I've seen that state before, where actually you haven't, because it is a hash collision in this Bloom filter, and then you conclude, well, I don't have to test that again, and then, okay, you get some incompleteness, but not nearly as much as when you keep revisiting the same states over and over. So can you speed that up? So what if the number of execution paths typically is tremendously large, right? It can be billions and billions of execution paths. You really want to statistically sample that space, even if you cannot be exhaustive, which generally you still won't be able to do because you simply run out of time. What if you want to increase the odds that you actually sample the majority of that search space? So in any case, you're in a territory here with testing that is vastly beyond what you can achieve with MCDC coverage, like 100% coverage. You're going vastly beyond that point. So the question is, can you actually speed that up too? And the answer is yes, because all these tests are independent and can be performed independently. They all start at the initial state. They pick a random path through the graph with recall, right, to avoid revisiting states over and over. You can do a form of swarm testing, what we call swarm testing. So basic methodology is here. You have this huge search graph. You want to use as many search engines as you possibly can and put them in different places of this huge search graph and have each one maintain some amount of recall, maybe with a Bloom filter. Right? They're all very small search engines using a small amount of memory. And you pick many of them, hundreds, thousands, tens of thousands, millions, and you let them search the graph. You give them as much time as you have available. Could be a week, it doesn't matter. You're guaranteed to have coverage that exceeds what you can achieve with any other method by an enormous amount. And I'll show you some examples of that in a second. So within each search engine, since they're all in different parts of the graph, they randomize their search to optimize the chances that you cover the entire graph. Now, I've been talking to Google about using this type of technology. And they told me, well, if you want to use this on our network, the minimum that we will consider for an experiment is 1 million CPUs. And actually, if you start looking at that scale, If you want to run an experiment with 1 million CPUs kicking into action and doing these searches, you have to start worrying about power usage. Like, so if you suddenly start up all 1 million jobs at the same time, you have a dip in the power grid, and that uses megawatts of power in their systems. So that you start planning along those routes. Couldn't actually do the experiment with Google because the software that I want to try this on is ITAR, and they don't have a mechanism yet for protecting that kind of data. But the potential in this methodology is very significant, and the number of CPU cycles that you have access to, that every single one of us has access to, in building flight software or anything else, is just going to go up. Right? In the next 5 years, it's just going to go up. So now, if I say, well, you want access to, say, 10,000 CPUs to do this test, you may think, well, I don't have that. I need the time on a cluster, and some other mission will push me off the schedule. 5 years from now, this is not an issue. You have it from your desktop. You can just do it. Oh, is that a signal? Okay, so we did an experiment on MSL. We took the standard unit test suite from MSL for the non-volatile file system code. Target for test coverage was 100%, but everybody's happy if you get in the range of 95 to 100%. So this is for different functions in that module, the MVFS module. The test coverage of that was actually achieved. So 99.2%, in one case 100% over a particular file. The lowest is 63.08, and actually nobody had noticed that until I repeated that test, because in the original set of tests it was all above 95%. But then unless you keep repeating these tests, then things change. But the average was above the requirement of about 95% unit test coverage. Now, we took that exact test case to see how many different states are actually reached in the system. Right? So I said sometimes you keep revisiting the same states over and over, and it turns out we counted 35,796 different system states. Now the graph, the execution graph for this system is vastly larger than that, right? It may have 1 billion system states. So this sampling, of course, it samples the important executions, the nominal executions, and some predictable cases of error handling, but it is a very tiny sampling of the search space. If you can make this more thorough, if we would have made this more thorough at the time, we may have been able to avoid 1 or 2 anomalies that happened in flight on MSL. So there were only 1,175 revisits of these states, 35,700 some unique states. If you do random testing for about 5 hours, now of course this doesn't take 5 hours, this completes in about 40 minutes or so. If you do 5 hours of random testing on that same software, you visit about 400 million states. So that's already quite a bit more than what you do in this unit test with 95% statement coverage. About 4 million states and 50,000 execution paths. So here there are maybe about 100 different execution paths that were being tested. Now the graph that I show here is the fan out that I measure from each state in the random testing. So there's a lot of repetition there. But these are 400 million unique states. And so I measured here, the tester saw on average 2 successors, 1 or 2 successors for every state that it reached. Now I can repeat that run with the methodology with perfect recall that I just described, and then I get this. So after 5 hours of testing with a breadth-first search with a recall, not perfect recall, it was using a Bloom filter with 3 hash functions. So every state sets 3 bits, and you have to get a match on all 3 bits to declare a match on the state. Now I reach 745 million states and more than 50 million paths, execution paths. But you also see that the coverage is much more thorough. So now I see the number of successors of a single state to be in this entire range. So I populate that entire range, seeing up to 64 possible next steps in this system for every system state that I reach. So despite in the order of 98% statement coverage, the unit tests with this very good coverage metric that is a required target explores 3 orders of magnitude fewer states than either randomized testing, which is, as we've seen, not particularly effective as a strategy, or testing with recall. And clearly the testing with recall, if you have a 5-hour budget for doing the testing, clearly that's what you should do, right? That's the most thorough type of testing that you can perform. So there's one downside, is that to be able to test with recall of states that you have seen before, you do have to instrument the application. And that means that you have to be able to identify what the state is of the system so that you can remember that. And if you define the state inaccurately, of course, the accuracy of the test goes out the window, because you will match on things that are not relevant or fail to match on things that are relevant. Now, setting this up takes some practice. There are mechanisms for doing that. Depending on the complexity of the system, it can be rather difficult to identify where all the state is. We actually had a hard time identifying this for the NVFS module. But if you write your code slightly differently, it can be trivial. Kim Costello has a proposal for a language that he called SPOT that for different purposes, not for this purpose, but for other purposes, for the sanity of the code and the structure of the code, made it totally trivial to identify what the state is of a module, because it's all located in one particular location where you can say, well, this structure has the state of this module, and this is the size of the structure. You track that as the system state, and you're done, right? So you populate your Bloom filter with the contents of that structure. Trivial, right? So then it becomes very easy to deal with this one type of instrumentation that you have to do. If you do it, you can dramatically increase your test coverage, and with dramatically, I mean orders of magnitude more thorough. And as a bonus, if you do that, you can then also perform much stronger types of tests where you use logic, specifically linear temporal logic properties, to verify and prove things about your model that otherwise you have no chance of doing. So it's a formal methods approach that allows you to do this on actual implementation code in a test environment. So now I'll end with a quote from Alan Turing, just to give deflect some criticism and say, well, he thought so too. He says, well, randomization can be very useful if you're searching for a solution to a problem if you don't know quite what the solution is. So we're searching for a bug in a program. We don't really know where it is. You can't really beat random, right? Because you're not biased to where the bug might be. That's the end of my talk.
When you ran the experiment for the MSL code, did you find anything that hadn't been found in the unit testing?
After the first anomaly hit on the surface of Mars, we ran this, and we found exactly the cause for that problem. Yeah. Well, the sequence is slightly different. First, the normal Tiger team was formed to identify what caused this particular thing. Once we knew what it was, we thought we should have found that. Like, we have this type of mechanism available, but we never ran it. And when we ran it, we found it, plus a few other things.
So you found it through code inspection, manual code inspection?
No, we found it with this mechanism.
You said the Tiger team found it.
Yes, correct. Rajiv
How long
figured
did
it out.
take the Tiger team to find it?
Rajiv knew very quickly. Like within a day, he knew.
Yeah.
Yes.
Humans are like that.
Yes.
Thanks. You mentioned that you could speed these up by doing the searches in parallel. Question I have is, before you can parallelize the search, is there some step you need to take to figure out like who's going to search which part of the tree?
Well, that's the randomization step. So you do a randomization for that.
And do they communicate at all with the
No.
the filter?
So
Do
it
they each
wouldn't
have their own filter?
It wouldn't scale. Yeah, that's an excellent point. But it would not scale very well if they had to communicate. So it's an embarrassingly parallel context. So they all run independently. As soon as one of them finds something, then in principle you can stop them all, but the others may find other stuff. But yes, it's completely decoupled.
Is the initialization stage kind of the bottleneck, perhaps? Like figuring out what all these million computers, which part of the tree each one would get? Is that kind of?
No, since it's random, no, it's not hard.
Okay, so they just randomly take it apart, so they may be redundant.
Yes.
In that parallelism. Okay. The other question I had was regarding, you had mentioned that Spot was a language that you could easily figure out what the states were so you could record them. Has anybody looked into how this could be done with Simulink, since people are talking about model-based in Simulink? I just bring this up as a question maybe for everybody to think about as well.
I don't know that, but somebody else might. Jeff, do you know?
Okay, thank you.
When you were posting the data for going through the swarm method, you had n number of parallelized processes with m amount of memory. Is there a formula those plug into for scaling up, or do you just kind of have a rough projection of if I have this much total memory available, I can run this many operations?
Well, no, I don't. Actually, that would be useful. That's true. But my thinking is you grab all the CPUs that you can, right? So the limit is not in your formula saying this. More is better, and since the number that you would need for exhaustive coverage goes up exponentially with the size of the graph you're searching, you can never have enough, right? So you grab all the ones you can get. So what we actually did for the MSL application was we used a 64-core computer and then repeated. So over many days, each time you do 64 runs at a time repeatedly until you come up to the numbers in the thousands.
Any other questions?
So, have you thought about applying any sampling to the number of states? For instance, you identify all the states. You're trying to do every single possible state testing, right?
Yes.
At a certain point, maybe in the future, where there might be way too many,
we're there, yes.
or restriction of time.
Uh-huh.
Have you thought about using like some type of sampling on that, and then calculate like a confidence level?
Oh, that's a good point. Yes, under certain cases you can compute a confidence level. But the sampling is already statistical. It's statistical sampling because of the randomization. Mm-hmm. Of course, near the top of the tree, you get a lot of overlap of all these, but as soon as they get down in the execution path, it all spreads out as best as you can theoretically make it, because it's random. It's not biased or guided.
Okay.
Yeah.
Thank you, Gerard.